18y. So.
And 18y. All right, and the gradient of g. Okay, so now this gives us a system of equations to solve, to find this point x naught, y naught, if it exists. So, for a point x, y to be a constrained max or min, then here's what we need to have happen. We need 8x to be equal to lambda times 2x minus 2. So we're just matching up the components of the gradients. And then we need 18y to be equal to lambda, and then we have 2y minus 2. All right, so these equations come from this. But we also have to make sure that the point xy itself satisfies the constraints. So we also need that, x squared plus y squared minus 2x minus 2y minus 2 is equal to 0. So gradient of f being a combination of the gradients of g, of the g's, we only have one here, and the constraints themselves to find a system of equations that you now have to solve. Okay. Oh boy. I still messed up because I was changing my mind here and there as to what I wanted to use for my constraint. I ended up switching constraints in midstream. This problem is null and void.
All right, cut.
All right,
Cut.
done.
Major.
No promises, obviously.
So this example is bad.
Unfortunately, yes, I'd have to go back because what happens is, in order to solve for a constraint earlier, so yeah, so I changed horses in midstream. All right.
So on our notes, does it reflect that error also on the lecture you handed us?
So the point is, on page 4, the last equation is bad. The very last one. So everything prior to that point is valid. And then, so the remainder of that example is flawed because of that. Yeah, so I'm just going to do the next one, which is independent. All right. Wish me luck. Because this one has two constraints. In fact, one of the problems in the book, in Marsden, that I did not assign, because the even number one, it was flawed. So, it's not just me. And now we have two constraints. We have x squared plus y squared is equal to 1. We're in free space, so this is now a cylinder. Let's find this equation. And then we have a second constraint, 2x plus z is equal to 1. So what kind of object is that going to be? Technical term again. What kind of object does this kind of equation describe? Free space.
It's just a simple line.
No. What?
Line.
It's a plane. If you have two linear equations in free space, you get a line. Yeah. So if you have n minus 1 equations in n-dimensional space, it's a line. But we're in free space, we only have one equation, so it's a plane. All right. So now, gradient of f. Can't mess that up. And then, so g1 of x, y, z is x squared plus y squared minus 1. And that is equal to 0. That's one constraint. The other constraint is x to 2x plus z minus 1 is equal to 0. Now, I remember when I was writing this problem, I was trying certain constraints that weren't working out and putting something different. So the same problem could come up, but let's find out. So gradient of g1, remember we're in free space now. 0, okay. And gradient of g2, 0, 1. Yeah, that's a z. Yeah. Okay, so now we need the gradient of f to be the lambda 1 gradient of g1 plus lambda 2 gradient of g2. So now this gives us the following system of equations. Alright, so first we have the x components, gives us an equation. So 1 is equal to lambda 1 2x plus lambda 2 times 2. Then from the y components of all three vectors, we have 1 is equal to lambda 1 2y plus lambda 2 times 0. Then the z components, 1 is equal to lambda 1 times 0 plus lambda 2 times 1. And then the constraints themselves. So we still have, well, 1 is equal to x squared plus y squared. 1 is equal to 2x plus z. So now, when we had one constraint, we had, and two variables, we had three equations. Now we have three variables, two constraints, so that's 5 equations that x, y, and z have to satisfy. Now we have some terms in here that are 0, so I'll just erase those. Okay. So, bless you. So right off the bat, we know what lambda 2 is. No choice there, it's got to be 1. Okay.
Come in.
Alright, lambda 2 is equal to 1. So now, we take that.
Knock back. He's trying to tell you a message. Morse code.
Maybe he's trying to help me do a problem. Alright.
He's tracking the ball. Come on.
So now you plug that back in here. So we have 1 is equal to 2x lambda 1 plus 2. So 2x lambda 1 is equal to minus 1. We have 2y lambda 1 is equal to 1 from the second equation. So what does this tell us about x and y?
That's just the negative of the other.
Yeah, so x is equal to minus y. All right. But now, but now we have x squared plus y squared being equal to 1. So if that's the case, and x is equal to minus y, what do we have? What are the possibilities? And what? Now we get down to specific numbers here. So if x is equal to minus y, we can plug in minus y, x equal to minus y in here, so we get, oh, is that what you were saying actually? 2x squared is equal to 1, so y is plus or minus 1 over square root of 2. So then x is the opposite of that. X is minus plus 1 over square root of 2.
Minus plus.
All right, I'll write that differently.
It makes sense.
Yes, it does. But so we have 1 over square root of 2 minus 1 over square root of 2, or you negate both. All right, and now we just need z, but we can get z from here. So actually we need x, y, z. So 2x plus